Alright, so this problem states a model rocket was launched in the vertical direction. At the end of the powered portion of the flight, the rocket was 89.6 feet high and the rocket landed 16 seconds later after falling freely to the ground. And we are asked to determine the speed of the rocket at the end of the powered flight and the maximum altitude reached by the rocket. The first thing we should do is we should draw a picture of what we know for this problem. And for us, we have a ground. The rocket is launched from a ground during a powered portion of the flight and makes it to 89.6 feet. We are also going to say that the positive y direction is up, is going this way, and our positive velocity is also in the same direction as our positive y. So this portion of the flight from here to here, which is 89.6 feet, was powered. After the power was turned off, the rocket continued to go up until it reached a maximum velocity, and then it fell down. And when it fell down, it continued to fall until it hit the ground. And this is at 0 feet. And the time it took from the end of the powered flight to go up and hit the ground was 16 seconds. So we're asked to determine the speed of the rocket at the end of the powered flight, which is right here, our velocity right at this point, and this is going to be our initial velocity. We're trying to determine our initial velocity. If we look at the three kinematic equations we have a final velocity is equal to initial velocity plus acceleration times time. We have the final velocity squared is equal to an initial velocity squared plus 2 times the acceleration times the final minus the initial distance. And we also have the final distance is equal to an initial distance plus an initial velocity times time plus 1/2 the acceleration times time squared. And we have to figure out which of these equations we need to use. And the best way to do this is to write down what we have. We have an initial x, and this is 89.6 feet. We have a final x, and this is 0 feet. We don't know our initial velocity because it's what we're solving for. And we don't know a final velocity because we do not know how fast the rocket ship is falling when it hits the ground, at the instant it hits the ground. We do, however, know an acceleration, and because this is gravity, we know our acceleration is going to be acting in this direction, and it's 32.2 feet per second squared. This is a point, 32.2. Now, we call it negative 32.2 feet per second squared because it opposes our positive y and our positive velocity. It's going the opposite direction, so it's a minus sign. And we also know t. T is equal to 16 seconds. And we know we're solving for this, so our equation has to have a v0 in it. So if we go through our equations, we can look at what we're solving for and try to determine which equation to use. If we look at this first equation, we don't have a final velocity, and we're trying to solve for v0. So we have two unknowns in this equation, so we do not want to use this equation. If we look at this next equation, we don't know our final velocity, and again, we're trying to solve for v naught, so we don't want to use this equation either. Now, when we look at this last equation, we know a final x, which is 0 feet. We know an initial x, which is 89.6 feet. We're solving for our initial velocity. We know a time, which is 16 seconds. We know our acceleration, which is minus 32.2 feet per second squared. And we know our time again. So if we put all the information we know into this equation, and we get 0 is equal to 89.6 plus v naught times 16 plus 1/2 times minus 32.2 times 16 squared, and we solve for v naught, we will get v naught is equal to 252 feet per second. And this is our answer for part A. Now part B asks us to figure out this maximum velocity reached. So when we try to figure out this maximum velocity reached, we just care about this part of the flight. We don't care about what happens after the flight falls back to Earth. So we just want to use the portion from the end of the powered flight to when it reaches its maximum velocity or maximum altitude. And again, let's write down the information that we know. We know a final position is what we're solving for. We don't know what this is. So our final position is a question mark. Our initial position is this 89.6 feet. Our acceleration stays the same. It's minus 32.2 feet per second squared. Our time, we don't have a time. We only know the time it takes for this entire flight. We don't know the time it takes to get to a maximum altitude. So our time is unknown. Our final velocity, which is right here, is actually known. Once the rocket ship reaches a maximum altitude, it's not going higher anymore, and it hasn't started to go down anymore. So our final velocity is 0 meters per second. And the initial velocity we solve for in part A is 252 feet per second. And this is not meters per second, it's feet per second. So we go through our equations again and look at what we know. Do we know a final velocity? We do. Do we have an initial velocity? We do. And do we have an acceleration? We do. However, this equation is dependent on the time. We don't have a time, so again, we cannot use this equation. So let's go to the second equation. Do we have a final velocity? We do. Do we have an initial velocity? We do. Do we have an acceleration? We do. Do we have a x final? Well, this is what we're searching for. And do we have an x initial? We do, 89.6 feet. So this equation looks pretty good. One unknown, and we know all the rest of the information. So we look at this next equation. Do we have a x final? Well, we're searching for that. We have an x initial. We know our initial velocity, but we don't know the time it takes to go to this top point, so we cannot use this equation. So when we have to use this second equation, and when we plug in all our numbers, we get a final velocity. 0 squared is equal to 252 squared plus 2 times minus 32.2 times x final is what we're solving for, minus x initial, minus 89.6. And when we solve for x final, we get 1,076 feet. So this is the answer to part B.